Today we're going to talk about adjunctions. Adjunctions describe a relationship between a pair of categories involving a pair of functors and a pair of natural transformations. Now, here's the situation that we're going to have. This isn't the formal definition yet, this is just the idea behind it. If we've got a pair of categories C and D, we like to think about ways of comparing them. And as category theorists, we like to think about things a bit more interesting than equality. Equality is a very rigorous and not very imaginative form of sameness. Do I mean imaginative? Well, I've said it now. And we now know that we can have something a bit more forgiving, which is called isomorphism. And when the two things that we're comparing are categories, then we can have something even more lenient, which is the notion of equivalence. Well, adjunctions are even more lenient than that. They're not really saying that the two categories are the same as such, so much as that there's a rather interesting relationship between them. So, just like with isomorphisms, we're going to describe this by means of a functor going this way and a functor going that way. We're going to call this one F, and we're going to call this one G. And let's just think a little bit about what kind of relationships we can have described by these functors going in opposite directions. So the first thing we can think about is the notion of isomorphism, which says if you go there and come back again, you get back to exactly where you started. So going there and coming back again is GF, because that's the way I write the composition. And it's saying that it's the same as just sitting where you started the identity functor on C. But also, you can say that if you start over there, come here and go back again, you get back to where you started as well. So that's saying that FG equals 1D. You might be wondering why I've written it this funny way around with the identity on the left here and the identity on the right here. And of course, secretly, that's because I know what's coming later. But anyway, equivalence of categories is a bit like isomorphism up to isomorphism, because we're saying if you go there and you come back, you don't land exactly where you started, but you just land somewhere isomorphic to where you started. So equivalence is where GF isn't equal to the identity, but it's isomorphic to it, and FG isn't equal to the identity, but it's isomorphic to it. So finally, we can think about adjunction, where we have something even weaker than this. We don't have isomorphisms like this, but we just have a natural transformation here and a natural transformation here. So that is the idea of an adjunction. We have a natural transformation in this direction, which is going to be called the unit, and a natural transformation in this direction. The directions here are very important, and now we can see why I wrote the unit on this side here and the unit on this side here all that time ago. Of course, when we specify natural transformations like this, they can't just be any old natural transformations. We do, oh, that's supposed to be an isomorphism sign. We do, in fact, want to be able to manipulate these a bit as if they were more rigid notions of sameness. We still want it to be useful. And in order for it to be sufficiently useful, we need to impose some axioms on this, as you might expect. You can now test yourself to see how much of a hardened category theorist you are by seeing if you can work out all by yourself what the obvious axioms are here. Try that now. Okay, if you haven't been able to do it yet, I will now tell you what they are. I'm trying to wipe the board a bit more vigorously now, so I don't leave remnants behind. Is that better? Okay, good. Right. So there is some very strong directionality going on here. We're going to talk about F being left adjoint to G, which we'll write like this. I'll say more about the left and rightness later. This notation shows, with this little turnstile thing, that the F is the left adjoint and the G is the right adjoint. And here's the definition. An adjunction of F left adjoint to G is given by, I've got a grammatical problem. Have I? Because I haven't said what these functors are. Well, given functors like this, given functors like that, an adjunction, F left adjoint to G, is given by a pair of natural transformations traditionally called eta, which is the one that goes from the identity on C to GF, and epsilon, which is from Fg to the identity on D. Now I'll tell you a secret, which is that if I ever write an adjunction that isn't F and G, I can't work out what's going on, and I have to translate in my head to F and G, and that's the only way I can remember it. Okay, don't tell them I said that. Right, so what are the axioms? When you're trying to work out what the obvious axioms are in category theory, you have to look at how your pieces of data interact in two possible different ways. So, for example, let's have a look at starting with an F. Now, if we started with an F, we could sort of insert a GF. This is what this is about, which is incidentally called the unit. What the unit is about is inserting a GF. And what the co-unit, this is called the co-unit, not counit. This is about removing an FG. And so if we start with an F, we can insert a GF on the right. We couldn't insert it on the left because that would have given us something non-composable. And now we do that with F eta. And once we've done that, oh look, there's an FG that we can remove on the left. And so we do that by using an epsilon on the left, and we get back to F. But there was something else we could do, which was just sit on our F and not go anywhere. So that's the identity on F, and that's supposed to commute. Now, dually, and I'll explain what I mean by dually in a second, or maybe in an hour, you could start with G, and once you've started with G, you can now insert your GF on the other side. So you can insert GF on the left, which says eta, do eta G, and now, look, you've got an FG that you can try and remove on the right, and that should be the same as just sitting on G and staying as you were. So those are the two axioms. These are often called the triangle identities because, well, they're triangles. And that is the definition of an adjunction. That, I've spelled identity completely wrong. That's better. Just in case you're not very comfortable with diagrams of natural transformations, I'll show you how these work as diagrams on components, because of course this is just the commutativity of some components in the underlying category. So at X, we're saying for all X in C, we've got F at F of eta at X, GF X, epsilon F has its component at X being the component of epsilon at F of X. Here we've got 1 on F of X and F of X. So here we're going to say for all Y in D, this is what's got to commute. The component of eta at G of Y, G of Y, G of eta of Y, and GY. Now, there is another way of thinking about these if you happen to like two categories and diagrams of two cells, because you can write eta and epsilon actually as two cells. So here's eta, that's F and that's G, here's 1 as an actual 2 cell, and here's epsilon as an actual 2 cell. Hopefully I got those the right way round. In which case the first triangle identity says what? It says this. Here's eta and here's epsilon is supposed to be equal to 1 as a diagram of 2 cells, and the second one is saying and there's epsilon and there's eta. So that's an alternative way. That's the two categorical notation for writing these things down.
Is an eta or epsilon not?
Oh yeah, you're right. This is supposed to be an eta. You're supposed to look at the shape of the diagrams, not the actual label that I absentmindedly wrote in the middle of it. So the reason I like these is because they're very geometrically vivid. There's only one thing you can do to stick these together this way, and there's another thing you can do that way, and then it should be completely unambiguous. Is there anything else I'm going to say now? Well, there are only 38 seconds left, so I think I'll leave it there. Now we're going to carry on talking about adjunctions. Last time, if you've watched the last time, we defined an adjunction, and I'll be honest, we didn't exactly define it like this with the precise wording, but here is the definition of adjunction. An adjunction is given by a pair of functors equipped with specified natural transformations, eta and epsilon, the unit and co-unit, satisfying these two axioms, which are usually known as the triangle identities, well, because they're triangles. There we are. Now, that's one way of defining an adjunction. Another way of defining an adjunction is the other way around. And what we're later going to do is show that the two definitions are in fact equivalent. Now, some people think of this as a definition of junction and think of the other one as some kind of characterization. You can also think of the other one as a definition and think of this one as the characterization, but because they're equivalent. Matter, let's stop waffling for a second, and only a second, and show something else. Okay, so here's a different definition. Definition 2. An adjunction, again with F left adjunct to G, is given as follows. It's given by a natural isomorphism from, now it's between the morphisms from f of x to y, it's between these morphisms and the morphisms from x to g of y. Now where do these morphisms live? F, okay, I forgot to say where my categories and functors were going. It's going like this. So f goes from c to d, so f of x is going to be in d, so these are morphisms in d, these are morphisms in c. And that's a natural isomorphism, which has to be natural in x and y. Now, you're probably thinking several things at this point. One is, this has absolutely nothing whatsoever to do with the previous definition. Another thing you might be thinking is, what on earth does natural isomorphism mean here? What does natural in x and y mean? Usually you have a natural isomorphism between two functors. I haven't even said what the functors are. So this is a short way that we sometimes talk about natural isomorphisms when we can't be bothered, basically, to say exactly what the functors are because it can be a bit tedious. But if you look at this carefully, this is actually describing a functor in x, and it's also describing a functor in y. So what are the functors? What are the functors that are, what are the functors that are naturally isomorphic here? Well, there's one that takes x and sends it to this set here. Right, so this is in fact a functor. X is an object of C, and so this is a functor from C up to set. And the other one takes x and sends it to this set. So this is a functor from C up to set as well. And since they're both functors from C up to set, it makes perfect sense to ask for them to be naturally isomorphic. And on the other hand,
so you fixed the y there.
We fixed the y, yeah, there are actually two natural isomorphisms. That's why I've said natural in x and y. Really, there are two naturality conditions going on here. So the other one is sending y to, well, let's do this one first, I suppose, so here y is the variable. Another way of writing this functor is d of f blank y. That can't possibly be big enough to read, well, let's see. And so the other one, this one, is in fact going from D, because y is an object of D, and it's going to set, and this time it's not D op, because the y is on this side of the hom thing, and this functor is sometimes known as D of f of x comma blank, because that's where the variable is. And so on the other side, we've got the one that takes y and sends it to cx gy, and this is sometimes known as c of x g blank. So that's where the natural isomorphisms are. Are there any questions about that? Excellent. Now let's see, now that we've worked out what the functors are that we're asking to be naturally isomorphic, can we see what the naturality square is going to be? So I'll leave. Was it unhelpful of me to have run that off? I don't know. It might have been unhelpful for me, even if it wasn't unhelpful for you. So one of them is going to say that we've got a morphism for all morphisms f going from x to x prime, say. We've got, on the one hand, this is one possible answer for the functor. and this is another possible answer of the functor. And if you apply this d of f blank y functor to f, what you get, because it's a functor on the op, you get this thing here. So this is d of f of f comma y. Over here, you get your natural isomorphism that's given by this. Let's call this alpha. So this is alpha. It's a component of alpha anyway. And that takes us over to c of x prime gy. And this takes us down to c of x comma gy. And this is another component of alpha. So what's this actually saying? This is saying coming down here, it's saying take a morphism from f of x prime to y and somehow produce a morphism from f of x to y using f. And so that what you have to do that is you have to compose with f of x. So let's just have a little crib sheet over here. We're starting with a morphism from f of x to y, and we're going to use f of f, which goes from f of x to f of x prime, and so we're producing a morphism from f of x to y. Hooray! We landed in the right place. You see, you never quite know unless you write it out if you're going to land in the right place. And so what we've done here is we've pre-composed by f of f. So this functor can also be written as blank composed with f of f, because what we've done is pre-composed by f of f. And what we've done here, by the same token, is we've pre-composed by f. So this is the naturality square that has to commute. I wonder if I can leave it to the reader to figure out what the other one is, the natural in y. So this is what naturality in x means. Now I seem to have about 2 minutes left, in which I'm going to give you a hint about what on earth this has to do with the previous definition, where we had a unit and co-unit. Let me get rid of this naturality square. So remember before, what we had was a pair of functors going in opposite directions and an eta and an epsilon. So how can we produce an eta and an epsilon from here? Well, look, let's put y to be f of x. So if we take a morphism from f of x to f of x, which lives inside d of f of x, this set is supposed to be isomorphic to c from x to g f of y. So this is supposed to produce a morphism from, g f of x to g f of x. Right? This isomorphism is a correspondence between morphisms like this and morphisms like this. So what nice morphism do we have from f of x to f of x? Aha! We have the identity morphism. So if we take the identity morphism, transfer it across this isomorphism to something, we're going to use this to be the component of the unit, eta x. To get the other one, we're going to go backwards, and we say, let's put x to be g of y, right? So if we take something from g of y to g of y, which is in c of gy, across this isomorphism, it's going to correspond to something in f gy, comma y, across the isomorphism. So a morphism from f gy to y. What are we going to use here? We're going to use the identity on g of y, and that's going to send us to exactly the right kind of component we want to be a co-unit. So this is going to be called eta y. What we're going to have to do next time is, I can see this clock counting down. I've only got 30 seconds left, which means next time we have to show, first of all, that these really are natural transformations. Stop laughing, it's not that funny. And moreover, not only are they natural transformations, but that they satisfy the triangle identities. And that's going to be so much fun that we have to leave until next time. Adjunctions. So far, we've seen two definitions of adjunction. We've seen the one like this one, and we've seen the one like the other one, which had the natural isomorphism between some Hom sets. But I want to think about this one a little bit more. I promised that I was going to prove why those two definitions were the same, and I'm going to carry on promising that. But before we prove that those two things are the same, I want to talk a little bit about how it's related to monads, because it's just so much fun. I can't resist it anymore. So this definition says we've got a pair of functors and we've got a pair of natural transformations like this, called the unit and the co-unit, satisfying the triangle identities. Now, the other thing I haven't said is what any examples of adjunctions are. And some very nice examples come from some things we've been talking about a little bit already. For example, so here's an example. If you have the category of sets, I'm going to try really hard to get this the right way around. The category of sets over here and the category of monoids over here, we know how to start with a set and make a free monoid on it. Free. And we know how to start with a monoid and forget that it was a monoid and just take its underlying set. Forget. And it turns out that this is part of an adjunction. And there are other ones we can do as well. We talked about graphs and the category of small categories. And we've got the free category functor and the forgetful category functor. And that turns out to be part of an adjunction as well. And one of the things to remember is that free functors are left adjoint to forgetful functors. And this is nice for various reasons, and one is that quite often when we're doing free constructions, we want to say what it means really to be free. Sometimes we sort of know emotionally in our heart that it's free because we've just done things really freely, but that's not a very precise mathematical thing to say. Whereas here we can say that if it's left adjoint to a forgetful functor, that is a completely definable notion of free. You might be wondering how you remember which is left and which is right. And it's very easy to remember which is left and which is right, because left has 4 letters, and so does free. And so that means that free is left adjoint. Okay, maybe don't tell anyone I said that. Moving swiftly on, why were we talking about the free monoid construction before? We were talking about it because it gave rise to a monad for us. And there's no prizes for guessing what I'm going to say next. No, there is a prize for guessing what I'm going to say next, which is that you can feel like you're getting the hang of this stuff. What I'm going to say next is that every adjunction gives rise to a monad in a completely wonderful canonical way. So here it is. Every adjunction gives rise to a monad. Now, what do we have to do to define a monad? We have to give a functor, we have to give an underlying category, a functor from that category to itself, and, yes, a pair of natural transformations, eta and mu. That's funny. We've got a pair of natural transformations, and what's even funnier is that one of them is called eta. Could it possibly be because it's the same eta? Right. So what's the monad? It gives rise to a monad. So every adjunction like this, as above, so that's F left adjoint to G like this, gives rise to a monad. The underlying category is C on C. Why? So what's the functor going to be? Well, look, we've got a category C, and I'm saying that we want to give a functor from C to C. What possible functor from C to C is there? Well, there's the one that says do F and then do G, which, by the way, I write as GF. So that's a wonderful functor from C to itself. Now, let's call that T, because that's what we were always calling our monads before. What do we need? We need a unit that goes from the identity on C to T. Well, fancy that. T equals GF, and we've already got a unit that goes from the identity on C to T. So the unit is going to be eta, as before, from 1 to T, which is, of course, GF. Now, what about the multiplication? What does the multiplication have to do? It has to go from T squared to T. What's T squared? T squared is GF, GF. What's T? T is GF. So what we have to do here, well, we can remove this FG from the middle. And we've got a way of removing FG, because that's what epsilon is. So we're going to remove this FG from the middle using G epsilon F. So mu equals the natural transformation G epsilon F. and it goes from the right place to the right place, so that goes from t squared to t. And to finish off checking that this really is an honest-to-God monad, what we have to do is check the two axioms. So now let's check the two axioms, she says nervously, hoping that she can check the two axioms on the spur of the moment. Let's see what the first one is. So, maybe that was an unhelpful thing for me to work out. Sorry. Take a picture of the computer screen or something. So the axioms for a monad. There are the triangular ones, one of which says that if you do t to t squared by t eta, and then you come down via mu to t, you should get the identity. So what does that say in our case? What it says is, okay, t is gf, t squared is gf, and eta is eta. So what we've got here is gf eta, and mu is g epsilon f. Okay, let's stare at that really hard for a second and think, well, I never. It comes from one of the triangle identities. Because if you just hallucinate those g's away, put your g filter glasses on, you'll see that actually this diagram is just g of a triangle identity. Okay, done. Guess what? There's the other one as well. Oh, now I've got a complete blackboard disaster. Where am I going to put this? Should I just wipe this out? Should I put it on the top? Okay, the other axiom, the right-hand side one, says that if you put eta on the left and you do mu, you should also get the identity. Okay, now let's write this out. GF, GF, GF. I can feel my time ticking away. It's terrible. GF, am I going to do it in time? Am I? What's this? So this is eta, GF, and no prizes for guessing. Yes, it's the other triangle identity, because if we remove the f's from the right-hand side here, no, we've done something terribly wrong. No, we haven't. It's right. It's right. Remove the f's from the right-hand side. So this is the other triangle identity with f on the right. Phew. Okay, now I've got 1.5 minutes to do the multiplicative, the associative square. Finally, we've got t cubed goes to t squared goes to t goes to t squared goes to t. This is mu t. This is t mu. This is mu. This is mu. So we've got gf, 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 gf. Okay, what's up here? We've got g eta f, because that's mu, and then we've got an extra g of f on the end. Here we've got an extra gf on the left, and we've got g eta f. Here we've got g eta f, and here we've got g eta f, and I've got 1 minute to work out why that commutes. Well, it obviously commutes. I mean, it obviously commutes, right? We need some help from the audience. Why did this obviously commute? Well, look, what we've got is an eta living over here, and an eta living on the other side. And I think this is just saying that if you do eta and then eta, it's a naturality square. It's a naturality for eta. Stop the clock. Stop the clock. It's a naturality for eta. Naturality for eta. Because look. Why is it naturality for eta? Because it's g of naturality for eta. Because if you remove these two g's, you've got eta at
Epsilon.
Epsilon, it's naturally for epsilon. Epsilon at FGF, and this is epsilon at F, and these are morphisms, right? So this is G, this is F, G on the morphism, and this is the other one on the morphism. Stop, it's done. At the end of Adjunctions 2, I promised to prove that the two definitions we'd given of an adjunction were both the same. And then I manifestly chickened out of actually doing it because I got cold feet and wasn't sure if I could spontaneously do it. So I've now gone and warmed my feet up or something, and we're now going to prove that the definition we gave in Adjunctions 1 does correspond to the definition we gave in Adjunctions 2. So remember, in Adjunctions 1, we said that an adjunction was given by a pair of functors going in opposite directions, a pair of natural transformations, eta and epsilon, satisfying some unit, the triangle identities. And in Adjunctions 2, we said that an adjunction was bijection between these Hom sets that was natural in both x and y. So this is f being left adjoint to g. Another way of remembering this is this f appears on the left in the home set and the g appears on the right on the home set. And the first part of this is, as I said, there's a bijection between these two things, which means that for every morphism from f of x to y in D, there is a corresponding morphism from x to g of y in C. And I like to write that as, call it this sort of transpose, and you can write that as a bar. So given a morphism S over here, you would write S bar over there. We can't read that. S. I was trying to write it sort of secretly, an S bar. That's a disaster. Okay. But also, there's a correspondence in this direction, which says that if you start with one over here, it corresponds to something over here, which you might write as T going to T bar. And bar is the same as doing nothing whatsoever. And the point is, with natural isomorphisms, is it's not just the bijection between these two things, but the naturality tells us that it's some kind of sensible bijection, and it's really like, it's an instance of the Yoneda lemma going on here. It's telling us that all you have to look at is where the identity goes, and that gives you everything else. So I said in adjunctions too that these are the two naturality conditions. There's naturality in x and naturality in y. And the key thing to do here is to look at where the identity goes. So you can put y equals f of x here, put y equals f of x, and look at something, look at the identity on f of x. So where does it go over here? I'm writing this as transpose, and I'm writing this as transpose. And remember, we said that this is how we're going to try and define. If we start with this definition of junction, we're going to define a unit and co-unit, and this is how we're going to define the unit, because this is going to transpose to eta of x. So when we come down here, what we're going to get is eta x composed with f. And that says that this is the same as coming down here. So we're starting with the identity here, we're composing it with the map f of f, and then we're transposing it. So that's the same as f of f bar. The other thing we can do is we can put, have I got enough space here? We can start here and go that way. Because this is an isomorphism, we can go this way around the square. So we can put x equals g of y, and we can look at the identity on g of y. So we transpose it this way and we get epsilon at y. So down here we get epsilon of y composed with f of f is equal to, now we come down here, we just get f transpose. So we can do the same over here with this one as well. We can put y equals f of x and look at the identity here. And this time what we're going to get, this is again transpose here, so we get eta at x composed with gg, eta x, and that's equal to g transpose. Alternatively, we can start over here and go this way around the square, and we can put x equals, I didn't mean y equals f of x, yeah I did, and we can put x equals g of y and look at the identity on g of y. We transpose to get epsilon of y, and so here we have g composed with epsilon of y is equal to, coming down this way, g of g composed with the identity, so that's g of g, and then we come over here and transpose. So those are the four important equations that we get out of these two naturality squares involving eta and epsilon. So let's just recap. We're starting with this definition of a junction, and we want to make it into the other definition of junction. So far, I've defined the components of eta and epsilon. So it remains to show that they're natural and that they satisfy the triangle identities. So first of all, what does naturality say? I'm only going to do half of these things. So let's check naturality of eta, which has a square looking like this. G f of x. So we're given a map f from x prime to x, just like here, and we have this naturality square like that. Here's eta at x prime, and here's eta at x. So look, this is an instance of one of these things. Let's call them 1, 2, 3, and 4. So this is an instance of what? What's an instance of? It's an instance of this, right? It's an instance of 3. So what we've got is, oh, it made a funny noise. It's all right. We've got g f x primed g f f, eta x primed g f of f, and if we transpose this whole thing, right, this is according to 3, it's equal to, so you remove the G and you transpose f of f bar. Oh look, so if you transpose it, you get f of f. Now coming down here, we've got f, and then we've got eta at x. Now what's that an instance of? Oh look, it's an instance of this. This is also equal to f of f bar. That was a bit easier than I was expecting it to be somehow. They're both equal to f of f bar, so both sides of this naturality square are equal. So what did we use? We used 1 and 3. So to get naturality of epsilon, we're going to use 2 and 4 in exactly the same way. I'll leave that to you. Now we can do the triangle identities. The first triangle identity has this in it. You've got to do G, f of x, which is eta of x, and then you remove the fg by doing epsilon at f of x. And that's supposed to be the identity. Well, let's have a look at this. Let's write it out in a straight line so that we don't confuse ourselves. That's f eta of x, eta at f of x. I mean, maybe you weren't about to get confused, but I was. So let's now see what this is an instance of. Well, it's an instance of this. Look, where eta of x is f. So what this is telling us is that that is equal to eta of x transpose. But what's eta of x transpose? It's the identity, because that's how we got eta in the first place. And that's exactly what we want. So that came from 2. And I do believe that the other triangle identity is going to come from 4. So I'll leave that one to you. So what have we done? We've constructed natural transformations eta and epsilon and showed that they satisfy the triangle identities using these naturality squares. So to do it the other way around, we'd have to start with, what would we have to do? We'd have to start with eta and epsilon satisfying the triangle identities and construct a natural isomorphism like this. Now I'm hoping that you can see how to do it, because I don't think I can do it in the remaining time. You construct this natural isomorphism by doing this entire process backwards and prove that these two things are natural using all these things backwards. And I do believe, is there anything else I should say at this point? I think that's all I was going to say today. So there it is. In Adjunctions 3, we showed that every adjunction gives rise to a monad. Now, you might think to yourself, what about the other way around? Does every monad give rise to an adjunction? And that turns out to be an excellent question. And the answer is yes. And moreover, the answer is a very nice kind of yes. And it turns out that 2 different solutions were found to this, more or less at the same time. One by Kleisli and one by Eilenberg and Moore. And one of them turned out to be initial and one of them turned out to be terminal. Isn't that nice? So initial and terminal in what, you might say? Well, it turns out that given what? Given a category C, there is an entire category of adjunctions giving rise to the same monad. Did I say that right? No, probably not. Given a monad on a category C, there's an entire category of adjunctions giving rise to it. And this category always has an initial object and a terminal object. And we'll show what those are. And so what that means is that given any other adjunction giving rise to that monad, you can sort of pin it down in relation to the initial object in the category and the terminal object in the category. So let's see what I'm talking about here. Given, so the question is, given a monad T on a category C, is there an adjunction giving rise to it? So remember, given an adjunction F left adjoint to G, it gives rise to a monad GF. So that's what giving rise to means here. Now, we've seen the category of algebras for a monad T. And it turns out that this is the terminal object I was talking about among all adjunctions giving rise to the same monad. So we can use this to construct a very nice canonical adjunction that gives rise to this monad. This turns out to be the terminal solution to this question, which is why the category of algebras for T is often also called the Eilenberg-Moore category. So we've seen the category of algebras for T, which we can also write as this, C with a T up there to show that it's sort of based on C somehow and constructed using the monad T. And the reason that we're going to do that is that secretly later, for the Chrysley category, we might write it there with the T at the bottom to show it's somehow the dual of this thing. So what we're looking for in is a junction. We're going to have an adjunction like this, which we might write as F upper T left adjunct to G upper T to show that they are the canonical ones. I'll probably drop those upper T's in a second because when we're proving it, we're going to be using just F and G and assuming that it is this F and G I'm constructing. There, that was a ramble. So the point is, let's just think for a second about one of our key examples, which was the example of the monad for monoids. And here you can think to yourself set, and here you can think to yourself monoids, the category of monoids. And here we had the free monoid construction, and here we had the forgetful functor that took a monoid and went back to its underlying set. And this is going to guide our way through forming this adjunction, because what we're going to do is we're going to make an algebra freely, and we're going to start with an algebra over here, and we're going to forget back down to its underlying object, C. So it's easy to construct G. G is easy, because it's going to go from CT to C like this. Remember, what does an algebra for T look like? It looks like an underlying object A together with an algebra action evaluating all the operations in here and sending them to here. So in the monoid case, this is the underlying set of the monoid. This is the free monoid on that set, and and then this evaluates where all those operations actually end up in the underlying set. So in this case, we wanted to take what? We wanted to take the underlying set of the monoid. So how do we take the underlying set of the monoid? It's this underlying object. That's a perfectly good functor from CT to C. On the other hand, how are we going to make the free thing? Well, if we start with an object in A, what can we make as an algebra here? We're going to express it as an underlying object together with an action. Now let's just think very hard about the monoid example. How do you make the free monoid? And remember, we want to express the free monoid as an algebra for T. What's the underlying set of the free monoid on A? Anyone? Anyone? Yes, it's Ta. Right? And so that's the underlying set of the free monoid on A. So to make an algebra on it, we've got to have some kind of action from T squared A to Ta. What have we possibly got? What could it possibly be?
The product.
It could be the multiplication, right? So now what we've got to do immediately is check to show that that really is an algebra. Okay, now I've run out of space. Typical problem. I can now just get rid of this. So this is our supposed algebra. Let's check that it really is one. Check. We're going to check that mu A gives an algebra for T. So what do we have to do? There are two axioms, remember. There's the triangle, which says this. You do eta A, eta. This is our underlying object, so it's got to be Ta, eta at Ta. And then we do the algebra action. And blow me down, it's one of the monad axioms. Fancy that! What a coincidence! Of course, it's not a coincidence, it's all very beautiful. And the other axiom is we've got to start with T squared A, and on the one hand we have to do, I've done it again. It's T cubed A, because it's T squared A, where A is the underlying object, so our underlying object is Ta. So it's T squared of Ta, which is T cubed. And now we've got to do, on the one hand, T theta. Well, what's T theta? That's theta, so this is T mu. And on the other hand, we've got to do mu T. So this takes us down to T squared A. And then we have to do theta in both directions. So this is theta, and this is theta. And well, I never! It's the other monad axiom. Fancy that! So that shows that it really is an algebra. Fine, so it shows that we have defined a functor going this way and a functor going the other way. So the next thing we have to do is define, well, we could do this in various ways, but one thing we can do is define an eta and an epsilon for this adjunction. Where are we going to do it? Goodness knows we're going to do it. Sorry, I just rubbed it out. Never mind. So we now need to define a unit and co-unit. Okay, so the unit theta has to go from G. It's got to go from 1 to GF. So now let's think about this very carefully. This is 1 on C and it's going to GF. So we've got to have on components. We've got to have something from A to GF of A. Now what's GF of A? F of A is this mu thing, right? And then to forget, G is the forgetful thing where we forget down to the underlying object. So that's just TA. So this is TA and this is A. So what could we possibly have as the unit? Well, fancy that. It could just be the unit for the monad. And now I've got some slightly strange notational problems because I've got eta and eta. Well, it's a coincidence that isn't very coincidental. Oh, what should I do? Okay, this is the unit for T. And now what about the co-unit? We need epsilon at some algebra. So this is epsilon on, say, TA to A. And it's got to go from FG of this algebra to the algebra. So it's got to be a map of algebras. Now what's this? What's FG of this thing? This is first you forget down to A and then you do the free thing on it. So it's the free algebra on A, which is given by mu like this. What's this? Well, that's just that. So what possible morphism could there be going from there to there? Oh, well, fancy that. We could put theta in here. I mean, if you look on the board, there's only one single... Uh-oh, I've only got 30 seconds left. There's only one morphism going from TA to A. So we're going to put theta there, and then we have to check that this really is a morphism of algebras, which means that this diagram commutes. Does it commute? Yes, it does. It's the second algebra axiom. So I'll leave it to you to check that the triangle identities commute. Last time we talked about the Eilenberg-Moore category and the fact that every monad gives rise to an adjunction via the category of algebras, otherwise known as the Eilenberg-Moore category. This time we're going to give the other answer, or another answer to that, and show that there's another way of getting out an adjunction that gives rise to a monad. And this is the Kleisli category. So what we'll do this time is define the Kleisli category, and probably what we'll do next time is show how to give the adjunction. Kleisli category of a monad, T on C, has, oh, by the way, this category is sometimes called Kl T, that's KL, and it's also sometimes written C sub T. Remember last time we had the Eilenberg-Moore category, which was the upper T, and this will be the lower T. It's kind of the dual situation and very, very related. Okay, so what are the objects of this category? Well, the objects are in fact just the same as the objects of C. What are the morphisms? Well, the morphisms are obviously going to be a bit more exciting. For the Eilenberg-Moore category, it was a little bit more complicated to find the objects and very much less complicated to find the morphisms. This time it's the other way around. This is sort of one of those conservation of complicatedness things. The complicatedness has to be somewhere. Right. So a morphism in the Kleisli category from A to B, the morphisms in here are defined to be the morphisms in C from A to TB. And to be clear about this, I'll write these as morphisms A to B with a line through them so that we know what we're talking about, where these are just ordinary morphisms like that. So now we have to define composition and identity. So let's think about this for a second. Composition, we've got to say, given an F and a G, given a composable F and G, in the Kleisli category, we have to produce a map from A to C in the Kleisli category. So of course F is secretly, it's a map from A to TB, G is a map from B to TC, and we're looking for a map from A to TC. Okay, stare at this for a second and see how we could possibly come up with a map from A to TC. We can't just stick them together in the middle because they won't go, but what we can do is we can hit this with T. We hit it with T, and now we haven't quite landed in the right place, but mu is now going to come to the rescue, because if we stick mu on the end here, it's going to take us back down to TC. So we've got a map from A to TC, which is exactly what we wanted, because that's the form of a map A to C in the Kleisli category. Okay, so that's what composition is. What are the identities going to be? So for every object A, we need a map in the Kleisli category from A to A. And of course, that's a map in the actual category from A to TA. What could it possibly be? What could it possibly be? Yes, it's going to be eta, the unit for the monad. Okay, so composition comes from mu, and the identities come from eta, and no prizes for guessing. Well, I shouldn't say that. I should say there's some fantastic prize for guessing that the axioms for a category are going to come from the axioms for a monad. So let's check what we've got to do. We've got to show that this composition is associative. And in fact, the hardest part of this is writing down the thing that we have to show. But we're going to remain calm and write it down very slowly. So on the one hand, we're going to start with F from A to B, G from B to C, and H from C to D. Okay, so first of all, let's compose F and G first, and then compose it with H afterwards. So composing with this part is exactly what's down here, right? So first we do F, and then we do T of G, and then we use mu to get us back down to the right place again. Okay, and now we're going to compose this whole thing with H, so we've got to do T of H, and then we've got to use mu to get us down to the right place. Right? Fine. Now, the other thing we have to do is we've got to do H composed with G composed with F. So let's just do H composed with G first. H composed with G, we start with G, and then we do T of H, which takes us to T squared of D, and then we use mu to get us down to the right place again. Okay, now, I didn't really write that far enough along, whoops. We've got to compose it with F. And to compose it with F, first we've got to hit this entire thing with T. Okay, so let's hit the entire thing with T. T squared H, T cubed D, T mu D, and T squared D. And then we stick F at the beginning and mu at the end. Right? So that's what the other association is. So what we've got to show is that this chap here is the same as that one there. So how are we going to do that? Well, let's somehow write them closer together. Let's get rid of this. And let's have a look at this. So what we've got to show is that this is the same as that. But oh look, it's definitely the same all the way up to here. Now let's just fill it in, because it helps me anyway when I'm trying to show that a diagram commutes, to have it as an actual diagram. So here's T squared of H. Here's T mu D, which goes to T squared D, and here's mu D. Okay. Now we can sort of see maybe there's a mu here and a mu here, and it wants to be a naturality square. And if we change this around here, it will be a naturality square. If we do mu at TD, and can we do mu that? Can we do that? Well, look, this is an axiom for T, the monad. That's the associativity square, and this is now a naturality square for mu. So, hurrah! We've actually got the associativity that we want, and it came out of the associativity square. How long have I got? All right. For the identities, well, I'll leave it to you, but you can probably work out by now that the identities are going to come from the other two monad axioms, because there's a left identity and a right identity in the category, and they're going to come from the left and right unit axioms for the monad. Now, the thing I really want to say about the Kleisli categories, you might be thinking, what on earth is this thing? What has it got to do with anything? Well, the way to think about it is to think that it's really just the category of free algebras. Last time we had the category of all algebras, and we showed how to construct free ones and found the adjunction like that. This is really just the category of free algebras. You might say to yourself, wait a minute, the objects are all the objects of the category. How can that possibly be? Well, think about the morphisms for a second. A morphism from A to TB. Now, if T is given by an adjunction, GFB. Let's just think about any old adjunction giving this. Then the map from A to GFB under the transposition is really just corresponding to a map from F of A to F of B. And we have a perfectly good adjunction giving rise to this T. We gave it last time. It's the one going to the category of algebras, right? So here's the free algebra, here's the forgetful functor. So this is saying that a map from A to TB, which is a map from A to B in the Kleisli category, is really corresponding to a map between the free algebras in the free algebras that we got from doing this free algebra construction. So what's going on here is that secretly you should think of this object A as really being the free algebra on A. So you can think of A as really being the free algebra, which remember is given by mu, like that. And if you wanted to be really technical about it, you could literally take the subcategory, the full subcategory of T-alg, whose objects were the free algebras, and show that that category is equivalent to this category. It's just two ways of presenting the same thing. So hopefully you've got an idea of why you should think of the Kleisli category as the category of free algebras, and even more hopefully, you might be able to see how there's going to be a canonical adjunction giving rise to T, because really it's just part of this adjunction that we did last time. Today we're going to construct the adjunction that comes from the Kleisli category. Now what did I mean when I said that? We started with a monad T on a category C, and we've constructed the Kleisli category for T, and I'm now going to show you that there's an adjunction that gives rise to the original monad that we started with. So we've got the Kleisli category CT, and we've got the original category C, and what we're going to construct is a monad like an adjunction like this, which I'll call F lower T and G lower T, that gives rise to T. What does it mean to give rise to T? It means that GT FT equals T, and that the unit and the unit and co-unit give rise to the right unit and multiplication. And remember that before we had an adjunction giving rise to T that came from the Eilenberg-Moll category. So how are we going to construct this? Remember that CT has the same object as C, but it has slightly funny morphisms, and that secretly you're thinking that it's the free algebras that came from this construction. So in order to get the functor going in this direction, what we want to do is think we're going to send it to the free algebra. But remember what I said last time, an object of this is really to be thought of as the free algebra on it. So on object, this functor is going to take A and just send it to A. What's going to be different is what happens to the morphisms. So on morphisms, we're going to take the morphism A to B. Now where does it have to go? It has to go to a morphism A to B in the Kleisli category, which remember is actually a morphism from A to TB. So how could we possibly get a morphism from A to TB out of there? Well, our only hope is to hit the entire morphism with T and then stick an eta on at the beginning. So that's how you get that functor. In the opposite direction, what we want to think secretly is we take a free algebra here and we send it to its underlying object, forgetting that it was an algebra. Now remember that A is really the free algebra on A. We're supposed to be secretly thinking it's the free algebra on A, in which case when we take the underlying object of it, what's the underlying object of the free algebra? The free algebra is that, remember? So the underlying object is TA. So on object, A is going to go to TA. And what about on morphisms? Well, a morphism here from A to B is really a morphism from A to TB, and so this has to go from TA to TB over here, because this was really a morphism from A to B. So how can we possibly do that? What hope have we got? Well, our only hope again is to hit it with T. We have very few tricks in this game. We just keep using them over and over again. So this goes from TA to T squared B, and then we use mu afterwards to get back down to TB. So that's a perfectly good functor. This is a perfectly good functor if you check their functorial. And then it remains to show the unit and the co-unit. Well, probably you can see what's going on here. This is, I didn't mean unit. Did I mean unit and co-unit? Yeah, I did. Well, here's the eta and here's a mu. Now, where should I put this? Where should I put this? Where should I put this? I think I'll put it up here. So the unit has to go from A to G F of A. Okay, so what's G F of A? Well, F of A is just A, and G of A is T of A. This is eta A, so we've got to go from A to TA. Oh, it's just going to be the unit for the monad is eta. I've got that notational thing again. What about the co-unit? The co-unit has to go from FGA to A. Well, what's FGA? GA is over here. It's TA, and then when we forget again, we just don't get anything whatsoever. Okay? TA, and this is A, and you might think, uh-oh, what's going on? Except, of course, this has to be a morphism in the Kleisli category. This co-unit, eta A, is a morphism in the Kleisli category. So what we actually need is a morphism from TA to A in the Kleisli category, which is just a morphism from TA to TA in the actual category. Well, that's not very difficult. That's going to be the identity on TA. So then you can check the unit and co-unit are satisfy the triangle identities. And you might think, well, what's going on? There's an eta here and an identity here. But it's all going to come out in the wash, just about. Because remember, when we compose morphisms in the Kleisli category, you do all sorts of funny things to them, and you use mu's, you stick mu's on all over the place. So it's all going to come down to the axioms for a monad involving eta and mu, and I just don't think I'm going to do it on the blackboard right now, because I want to say a little bit more about how the Kleisli category and the Eilenberg-Moore category interact. So the point is that given the monad T on C, there's a whole category of adjunctions giving rise to it. So here's one possible adjunction giving rise to it, and here's another possible adjunction giving rise to it. Right? And what's a morphism in this category going to be? Well, you guessed it. It's going to be a morphism up here, that is a functor up there, making the left adjoint parts of this triangle commute and making the right adjoint parts of this triangle commute. And in this category of adjunctions, so this is we get a category, we can call it adj T, which means the category of adjunctions giving rise to T. We have an initial object, which is the Kleisli category, and we have a terminal object, which is the Eilenberg-Moore category. And so what we've got is a situation where over here we've got this adjunction we just constructed, and over here we've got the terminal one which we constructed before. So this is F lower t, G lower t, this is F upper t and G upper t. And then you can say, given any other adjunction, here's some random adjunction that also gives rise to it, there's a unique map here, induced by the fact that this is the initial object, and there's a unique map here, map of adjunctions, induced by the fact that that's a terminal object. So you've got this sort of tug of war going on where you fix these ends and you know exactly where this is by looking at these morphisms. And the interesting questions that you might want to ask yourself are, when is this category actually the same as the initial object, and when is it actually the same as the terminal object? And that is a question I mentioned earlier, which is the question of monadicity. So you look at this comparison map that compares this to the category of algebras, and you say to yourself, how close is my category D to being actually the same as or equivalent to this category of algebras? So the question is, given an adjunction F left adjoint to G, Is D equivalent to the category of algebras for the monad? And that's what monadicity is. So there are several ways of saying this. You can say that the category D is monadic over C, if this is true, which means you can express everything in it as an algebra for the monad. Or you can say that this adjunction is a monadic adjunction, which means that when you take the category of algebras, you just sort of basically get the same adjunction that you started with. And another way of saying it is you look at this forgetful functor, the right adjoint, and you say that G is monadic if this situation holds. And one way of thinking about it is that monadic adjunctions are particularly good kinds of adjunctions. They're very canonical. You know, this is a particularly canonical form of adjunction, that's a particularly canonical form of adjunction. And so asking for an adjunction to be monadic is abstractly asking for it to be particularly canonical. In practice, what it's asking for is for D to be really like a category of algebras. Why do we like this? Well, there are lots of reasons we like this. Categories of algebras are particularly well behaved. Perhaps we'll talk about this another time. They have very good features. You can get hold of all your algebras. You can get hold of all your algebras in particular ways. I can't possibly say anything coherent in the last 25 seconds after that. But categories of algebras, it's easy to construct. It's easy to construct certain things in them. It's easy to construct. No, I can't remember whether it's limits or co-limits. It's got to be limits. It's got to be limits. And before I say anything else that's wrong, I'll stop.